when we finished. We figured out that who was running the repair shop? Was it Charles? I think.
I believe it was.
Yeah, I think so. So in Charles's repair shop, right? If he has a car in for repair, there is a probability of 0.581 that it is a spark. Yes, no?
Yes.
Right? Whereas the probability that it's a Camaro was, I think that's a 0.41, is it not? It's less than 4%, or a little bit higher than 4%. Okay? We figured all this stuff, these two values out. I don't know if we figured out the probability of M given R. It'd be 1 minus that, right?
Right.
So what I'd like you to remember, okay, I have them written down right now, okay? These values right here, we talked about it, right? These are the a priori probabilities. Didn't we talk about this?
Yeah, I feel like you mentioned that. Yeah,
These are
I have
the
it written down.
Yeah, these are the probabilities of a specific type of car before we know about the repair information. That's why it's called a priori, prior. That's the prior probabilities. Okay. Again, Charles doesn't care as much about these numbers, right? Charles cares about these numbers because we said, well, he's going to make more money off a Camaro repair job than a Spark repair job, right? And we said, what are some of the reasons for that, right? So Charles would care about these numbers, the post, the God, what's the number, or what's the term? It's not the a priori; it's the actual probabilities. Okay. What is your conclusion if these numbers are correct? What is your conclusion about the quality of a Spark versus the quality of a Camaro?
Well, I guess just based off those numbers, it implies that the Spark is less reliable, but that's also based on like the sales numbers.
It most certainly is. It is. But it's still it's an even higher probability that Charles is going to see more Sparks in his repair shop than a higher percentage than actually sold, right? If the quality were the same in each car, then these numbers would match the a priori probabilities. Do you see that?
Yeah.
If the quality were the same. So, in other words, guys, you get what you pay for, right? You've heard that term before, yes, no?
Mm-hmm.
You get what you pay for. If you don't pay a lot of money for something, either you got a really great deal on it or the quality isn't there. Okay? And that's just the fact of life, I guess. Okay? Are there any questions on this example? Because we actually did a lot of different things on this example. Yep. Yeah. We said you missed Thursday. We said that a quarter of the Sparks are going to need repair, 0.2 of the Malibus, and 0.1 of the Camaros are going to need repair work. Okay, so this is the event R that a randomly selected car needs a repair. All right, and we used our information to generate a tree diagram, and from there we calculated the conditional probabilities. Notice that, and this is important, guys. Notice that we used the definition of conditional probability and the intersection here. We used that to flip the given conditions. This is probability of R given K. This is the probability of K given R. Okay. So we use this information, and that's actually going to lead to the first thing here that we're going to talk about today. Okay. All right. Any questions? Okay. Yeah. Yeah. You use this equation, multiply that, and then that gives this term here all by itself, right? Well, this term here all by itself, if you divide by P of R, you get this. Yep. It's just using the definitions of conditional probability and algebraically messing with things to flip the given condition. Okay. All right. Can I reboot the board?
Yes.
If you guys want, you can take a picture and throw it in the chat because I think there's a lot of information here that you might find useful. Got it? All right. I'm gonna clobber the board. Okay. Going once, twice.
You're good.
All right. I'll leave the Venn diagram up here. Because this example actually leads to our next definition and our next theorem. It won't work for the next example, though. Although I guess we could do a different Venn diagram. I assume these examples are helping you guys? Yes, no?
Yeah. This class, like, I understand it, but it also doesn't click as easily as other stuff.
I understand. I do. I when I was in school, a lot of professors didn't do examples, and that really, I didn't like that. I did better when I had examples right after the, you know, right after the theory.
What did they do instead of give examples? Just move on?
Move on. Either that or give an example of just some obscure. I'm trying to think of a good. They give you a theorem and then they give you an equation that might apply to that theorem, but they never really worked it out in a real life situation, and that was pretty true of, especially physics and stuff like that.
Mm-hmm.
It's like, just give me an example so I can see this thing in action, right?
Yeah. See it done.
Yep. Okay, law of total probability, which we've already used actually, but now we're going to define it. If A1, A2, A3, all the way out to A sub K are mutually exclusive events, then the probability of B equals the probability of B given A1 times the probability of A1 plus probability of B given A2 times the probability of, what do you think, guys? A2, right? All the way out to the probability of B given A sub K times the probability of A sub K. It's a way to, no, that's Bayes' theorem. And this actually can be compacted, and we're going to look at this in just a second, guys. This expression can be compacted as I equals 1 to K, summation thereof, probability of B given A sub I times the probability of A sub I. Okay? Guys, that's what we did here. That's how we found P of R. We actually used this in the tree diagram. If you recall, in our tree diagram, we had a node, so we knew this probability. This was actually K, right? Probability of a spark being sold, right? Yes, no? Then we had probability of a Malibu, and then we had probability of a Camaro, right?
Right.
So in the general form, this would be node A sub 1, okay? And we're saying that the theorem, or the law, sorry, says this is event B. We called it R, probability of a repair. But this isn't probability of a repair in general. This is the probability of a repair given the fact that it's a spark, which was, I think, 1/4. You think? Okay. So in our tree diagram, we said that, and this would be R given M, and this would be R given C, right? We added up this value here, and this value here to get the probability of R, which we're calling in the general form is the probability of B. Okay. Do you see the tie-in between this general form of the expression, the Venn diagram that we used earlier, and the tree diagram that we used earlier? You just add up these areas or add up these node probabilities in the tree. Does that make sense?
Yes. So this was when
Go on.
what value were we finding when we did this with the cars?
Probability of R, probability of a repair.
Okay, yep.
Okay. What we did was we added these three regions in the Venn diagram, right? Right, guys?
Yeah, and then okay, yeah.
Does that make sense?
Yeah.
And we found these probabilities to add up. We found these probabilities by doing this. We didn't call it B given A1 times probability of A1. We said in our example, find a different color for you. We said probability of R given, say, a Malibu times the probability of a Malibu, right? That's what we said in our example. But it's the same thing. You just, B is the event that it needs repair. A1 is a Spark or a Malibu or a Camaro. But here's the general form. Okay. Are there any questions on the law of total probability? Because what we're going to do next uses that. Talk to me.
Not at the moment.
I didn't
Not at the
understand
moment.
that. Oh,
No questions at the moment.
okay. Does anyone else have any questions? Crystal clear, right? Okay. How about if we do a theorem, then we do an example, then we'll see if it's crystal clear. All right. Can I reboot the board? All right. All right, let's get rid of this just for sake of argument. We're doing a midterm on Friday, right?
Yes.
Okay. All right. That's the important date for the week. So make sure you study your homework. Make sure you study chapter 1 and 2. Okay. All right. Bayes' theorem. This is named after Thomas Bayes. Okay. He was an English clergyman, mathematician kind of guy. I think he was in the late 1700s, early 1800s, something like that. Goes like this. The probability of some event A sub j given B equals the probability of A sub j intersect B. This is just the definition of conditional probability, guys, right? There's nothing new here, right? But this equals taking upstairs and only upstairs the probability of B given A sub j times the probability of A sub j divided by summation. This is the same thing we did for the law of total probability. Probability of B given A sub j, A sub I, sorry, not j, A sub I times the probability of A sub I. This is the probability. Can you guys see the orange?
Yeah, kind of.
Kind of.
Let me switch to hot pink. You can definitely see that. Yes, no?
Yes.
Better.
That's that. That's that. Yes, no?
Yeah.
Do you see that? Does everybody see what's going on here? It's simple substitution. But Bayes was the first guy to come along to do it, so therefore it's named after him. Okay? Do you see what Bayes' theorem allows us to do? Bayes' theorem allows us to flip the given condition. Okay? Instead of finding B given A sub j, we can find this. Okay? Are you ready to do an example?
Yep.
Okay. Here we go. I can get rid of this, right? Going once, twice. Okay, now, guys, does anyone have any children? Any kids?
Yeah, I got a couple.
Is that Chris?
Yeah.
Okay, are there any boys? Do you have any boys?
Yeah. We got one.
One boy? Is he active?
Yeah.
Okay, so you've already made a couple trips to the ER, yes, no?
Yeah.
How did I know? So, I'm just, you don't have to confirm or deny, Chris, but just go along with it if you would. Chris takes his, I don't know, football, soccer, baseball, basketball, something. I don't know, just screwing around in the backyard, right? If you did a lot of that when you were young, then you might have gotten a few bumps and bruises along the way. Yes, no?
Mm-hmm.
Right? And sometimes you need the bumps and bruises are a bit more serious. So your parents or Chris might end up taking his kid to the ER. And it's same is true for girls, of course. Girls get hurt just like boys. So let's say Chris's son, he's playing baseball or something like that, and he gets whacked in the wrist. Pretend, okay? He's hit by a pitch or something like that, gets whacked in the wrist by a baseball. Swells up like a balloon, right? So Chris, like a dutiful parent, what do you do, Chris? You put some
Take
ice
him to
on it,
the
right?
ER. Yeah.
Take him to the ER. Yeah, okay, all right. Really hurts, right? So you got to take him to the ER because it might be broken. And in case you're wondering, bone breaks are not something to be trifled with, really, especially in children, right? So what do? They do
an X-ray.
They do an X-ray, don't they?
Yeah.
I mean, they don't. You take your kid and he's holding his wrist like this, right? The first thing they do is not, okay, get the scalpel out, chop the hand open, see what's really going on inside there, right? That's not the first thing they do. Okay. They do a couple of tests, yes, no?
Mm-hmm.
They do a couple tests before they cut it open.
They do a couple tests before they cut it open. Okay. And the reason for that, I hope, is obvious. Tests are cheaper, right? An X-ray is far less invasive than cutting the hand open, right? Doesn't cause any discomfort really, except for, okay, put your hand flat like this. Oh my God, that hurts. Stuff like that. Other than that, it doesn't cause any discomfort. It's easier, right? So the test itself, guys, and this is what's important. That's the point of the problem. The test of the example. The test itself gives us an idea of whether the condition exists or not. It doesn't tell us directly. Do you see that?
What do you mean?
What was that again?
Okay. If you do an X-ray, even if the X-ray is somewhat conclusive and the X-ray reveals a broken bone, X-rays are a bit of a stretch. Okay, they're not the best example, but I wanted to drive it home for everyone. Okay, let's put it this way. The doc comes back and says, we think a bone is broken because we can see a little line in the X-ray, right? Okay. And that will happen to you. I don't know if it's happened to anyone yet in this class, but it will happen to you, especially if you have kids. Okay. You get hurt, they take an X-ray. Well, it was kind of inconclusive. We think we see something, but we're totally not sure. Okay. So then they might do more tests, or if the condition is dire enough, they might just go ahead and do surgery. X-rays are a bit of a X-rays and MRIs and CAT scans are probably not the best example of this. But have you had a COVID test? Anyone?
Yeah.
When they do a COVID test, do you really think they're looking for the COVID virus itself? I don't think they
don't actually know what they look for.
Pretty sure
They're
they
looking
don't.
for the antigens or something.
Who said that?
Liam.
Liam, good job. Aren't they looking for the antibodies? I'm pretty sure they are. They're looking for your body's reaction to the virus, because the virus is too hard to detect. But I guess the antibodies, the antigens, or whatever they call them, those are easier to detect.
That makes sense.
Okay. Chris, I think you're the only one that has children, so I'm sorry. I got to pick on you a little bit. Is that okay?
That's cool.
If you're totally uncomfortable, you got to let me know.
No, that's good.
Your wife had I assume she had all the prenatal care with your children? Yes, no?
Yes. Yeah.
Okay, so she went in for ultrasounds and all that?
Yep.
Yep. Yeah, just like my kids, my girls and my daughter-in-law. So they the ultrasound, that's a test, isn't it?
Mm-hmm.
Right? Do you see that
Sure.
guy? Do you know what an ultrasound is? Does everybody know what an ultrasound is?
Yeah.
Yeah.
Does anyone not know what an ultrasound is? Okay, when you get married and you become fathers and start having kids, you'll know exactly what an ultrasound is and what it looks like and all that kind of stuff. I'm sure Chris, you're totally familiar with them and remember them well.
I remember paying for them. Yeah.
Well, it was a whole lot cheaper than having them rip your wife's belly open and checking the baby out.
Yeah,
I guarantee you it was cheaper. So when they did the ultrasounds, Chris, what exactly did they look for?
well, they were just looking at the size of the kid.
Okay. All right. Size of the baby. Abnormalities. Okay.
Heartbeat.
And by size, did they have did they have a tape measure that they put inside your wife's womb and kind of look at the implanted Stanley tape measure that they got from Home Depot?
No, they used the screen.
They used the screen, right?
Yeah.
They used the screen, took measurements off the screen. It is a test. It is not a true, completely 100% indicator. Do you see that, guys?
Yeah.
Okay. if they all sorts of cancers, they detect abnormalities in your blood. If you've to see if you've had a heart attack or not, don't they check for cardiac enzymes, I believe, in your blood? Pretty sure that's true. That's one of the first tests they do to see if you've had a heart attack. They check your blood because when the heart's under stress, it releases some kind of an enzyme into the blood. And they check for that. I'm sorry?
Troponin?
You'd have to tell me, not ask me.
That's it.
That's the heart enzyme they check for?
Yeah.
Okay. So again, it's a test. Do they know for sure whether you've had a heart attack? Well, they weren't there, so they don't know. But they're checking, they're performing a test. So, do you see, guys, that, I do have a story for you. I certainly hope you like the stories. My son, my daughter-in-law, went in for an ultrasound with their son number 2. They'd already had Peyton, also known as the P-Man. So they were expecting Trenton, known as the T-Man. And anyway, so Cassie had all these ultrasounds, and Tim was there and all that for them. But they came back with actually a pretty upsetting. They were very upset, you could tell. But ultrasound shows that Trent might have small, long bone syndrome. And this is obviously before he was born. Okay, I think it was at 6 months of pregnancy, and pregnancy is obviously, I hope it's obvious, it's 9 months. So she was about 2/3 of the way along. And what they did, they did exactly what Chris was mentioning. They took dimensions on the, because the image looks something like this, if I remember right. Chris, help me out. It's kind of a triangle shaped thing on the screen, right?
Yeah.
I remember that vaguely. Anyway, and then you got the baby, right? Arms, right? Torso, little feet, right? So they take dimensions, right, of the legs, arms, overall length, that kind of thing. Gender, if you want to know the gender of your baby. Anyway, so off the screen, this is the screen, guys. So they take these measurements, and if it's it's supposed to be a certain measurement, and they take ratios and all that kind of stuff, and they compare, and if the numbers are off, then they think that your baby might be suffering from dwarfism, right? And that's what they thought Trent had with Cassie. Well, the test was totally incorrect. It was Trent does not suffer from dwarfism. He'll probably be taller than his brother eventually. So anyway, the point is, guys, the test can be wrong because they are not examining the condition that you're checking for. They're not looking at it directly. Okay. So you ready to roll on the example?
Yes.
Yes.
Does anyone have a significant other or yourself or something like that? Somebody who's like a nurse or a doctor or in the medical field at all?
My wife's a nurse.
Ah, Chris, I'm getting a lot of mileage out of you today, buddy. What's her name?
Kate.
Kate?
Yeah.
I have a Katie, so that'll be easy. Meets with a medical rep representative. How do you spell representative? Who presents their new test for a condition. I don't know what the medical condition is. We'll talk about that later, okay? All right? Okay. Now, statistics show that 1 of 1,000 people in the population, and I don't know what the population is either, guys. Maybe it's suffers from small long bone syndrome. Maybe it's being a genius, right? Being a genius, having an IQ of like 100 and whatever the threshold is, that's a condition as well. Maybe it's having heterochromia, which is the condition where the two eyes are different colors. You ever meet someone that had a blue eye and a brown eye? I mean, they're perfectly normal, but their eyes are just two different colors. Well, maybe that's the condition. Maybe it's something far more serious. Maybe it's cancer. Okay. Maybe it's a heart attack. Maybe it's a COVID test. I don't know. Actually, that probably wouldn't. Well, I don't know. Okay. So in the population, 1 out of 1,000 people has the condition. Okay. All right. Problem is detecting it. Okay. Now the new test is 99% accurate. We're going to do a tree diagram, guys, so you need to follow the verbiage here. You need to follow the wording, but we're going to talk about it as well. New test is 99% accurate if the person has the condition. The test is 98% accurate. That's pretty good, actually, right? If the person doesn't have the condition. Okay? So, do you understand what's going on here? Does anyone not understand?
Makes sense.
Right? Now, what Kate's interested in is this. In the probability that a person has the condition given a positive test result. Okay? Why is that? Why would Kate be interested in that value? Think about what we just talked about, what the condition might be. Maybe a
'Cause if
broken bone. Go on.
If they have the condition, they need treatment.
Yeah. Kate's going to do something, or Kate's going to recommend that her, the doctor she works for or supports is going to do something if the test result is positive, right? Right?
Yeah.
If the X-ray or MRI or ultrasound or something like that shows a positive test result, for some kind of a bad condition, wouldn't this probability be pretty important because you're going to do something about it if you assume the person has the condition? You're going to take action, like Chris said, right? Yes, no?
Mm-hmm.
I mean, if the X-rays on Chris's son's wrist show that every single bone is broken, do you really think they're going to, well, every single bone in your wrist is broken. Take 2 aspirin and let me know how you feel in the morning. They're probably not going to do that, right? They're probably going to do surgery based on that X-ray result. So do you see why this is so important if you're in the medical, actually, if you're the person as well, right? The person being examined, right? This is really important, right? Actually, all the probabilities in this example are, but again, the doctors would be really interested in this. Yes, now?
Yes.
Okay, let's draw a tree diagram, okay? And then we'll work on figuring stuff out, all right? Can I here, I'll write the probabilities over here. The probability that a person has the condition is, in general, 1 out of 1,000, right? Yes, now?
Right.
Now,
Yes.
how do we quantify this statement right here? 99% accurate if the person has the condition. Well, the given condition is the person has the condition. Yes, no?
Yes.
Right?
Yeah.
That's the given condition. So this is a conditional probability statement. The given condition is that they have the condition. And if it's accurate, that means that the test is going to be positive because a positive result is interpreted as the person having the condition. Do you see that? Talk to me. Does everyone see that?
Yeah.
And the result, we can translate the second statement, right? The given condition is, that was a question.
Person does not have the condition.
Negative result.
There you go. Yeah, no, you both are right. You both answered both sides of the conditional statement, right? By the way, if you think this will never apply to you for whatever reason, you might have had can I get rid of this stuff now that we have the math down?
Yeah.
Okay. We're all guys here, so we all have a prostate, and one of the tests they do for a problem with your prostate is something called PSA, which I think stands for prostate specific antigen. And they used to put a lot of faith in that test. But I read somewhere that it's like 60% correct. Doesn't give you a lot of faith in the test, does it?
No.
Like, you would be a little concerned, right? I think what they do is it's more accurate if you don't have a problem, I think. So if it's positive, they do more testing. If it's negative, they assume you're good, unless your symptoms increase. I think. Okay, so here's the tree diagram, guys. somebody walks in off the street. They either have the condition or they don't, right? Correct?
Yes.
So what's the probability they have the condition?
One out of 1,000.
1 out of 1,000. So the probability that they end up in this node here is 1 out of 1,000. Of course, they don't know that. Neither does Kate. Neither do we. That means that the probability that they don't have it is 0.999. By that, guys?
Yeah.
All these numbers have to add up to 1, just like all the numbers in the next level have to add up to 1. Okay? This is where you guys need to get your calculators out, by the way. So, again, person wanders in, and Kate administers this test. This new test that is 99% accurate, 98% accurate, depending. The test is either going to be positive or it's going to be negative. Similarly, if the person doesn't have the disease, or the condition, I should say, the test is still going to be either positive or it's going to be negative. Okay? Right? Now, this right here, the probability of following this line here and ending up on this node is the probability of a positive test result, but it's given that they have the condition. Right? Because in order to follow this line, we already know that they have the condition. So that's the given probability. And this right here is the probability of a positive result given that they don't have it. Okay. Same thing down here. What do I write here, guys, along this line here? This line right here.
Wait, that's a
I'm sorry.
positive
This is a
result.
negative, 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 negative. Is that what you're saying, Brian?
Yeah.
Yeah, good catch. And this has the condition. I was jumping down to the bottom, wasn't I? I'm sorry. My bad, guys. Good catch. So what's this probability on this line here? You know what the given condition is, right? They don't have it. So it's the probability of a positive test result given that they don't have it.
So it'd be 0.02.
You're going to have, yes, that's the conditional probability. Actually, we can fill these values in. We can't fill them in at the nodes yet because remember, we have to multiply this value times this value to get the probability of a positive test result intersect. They don't have the condition. So we have to multiply these two values, right? And I think you get 0.1998, I think. Make sure you check that out. Verify that. And this right here is the probability of a negative test result given that they don't have it. What's this conditional probability down here, guys? Isn't this 0.98?
Yeah.
Okay. This positive test result, given that they have the condition, this is 99% accurate, right? 0.99.
Mm-hmm.
And the probability of a negative test result, if they have the condition, is 0.01. Okay. So the probability of a negative test result intersect having the condition is 0.00001, I think. Is that right? Yeah, that's right. This is the probability of a positive test result, and they have the condition. And this is going to be 0.00099, I believe. Lastly, this blank here, this is the probability of a negative test result, and they don't have it. And this is going to be, you got to multiply these two values. If I remember right, it's 0.9794, something like that. 92.
0.97902.
0.97902.
Yeah.
Okay. We have to carry out a lot of decimals here because of these two probabilities right here in the beginning. So we need to carry like 5 decimal points. Okay. Are there any questions on the diagram thus far?
No.
Yeah.
Everybody,
I'm not seeing where you're getting these numbers from.
which numbers? These?
The last ones.
These.
Yeah.
Oh, this is for example, the probability of a positive test result, given the fact that they have the condition, right? This equals the probability of a positive test result, and they have the condition, the intersection, right? Divided by the probability that they have the condition. Yes, no?
Yeah.
This is the definition of, right? So just multiply the probability of having the condition on each side, and we get the probability of the intersection equals the probability of having the condition times the probability of a positive test result given that they have the condition. So that's why we multiply, guys. We have these values: probability of having the condition, probability of not having the condition. We have those values. So we use that information and the conditional probabilities to get the actual intersections. Now, it doesn't give us the final result, but it gives us a start. Okay?
Okay.
Does that make sense? Now, how do we find this, guys? The probability, let me change colors because can you tell the difference between the purple and the blue?
I can, yeah.
Kinda.
Kinda. Okay. How about if I switch to teal? How about that? Is that a little better?
They all look the same to me.
How about this?
Okay, yeah, that's a little different.
All right. So the probability that a person has a condition given a positive test result, that's what Katie's interested in, or Kate's interested in, equals the probability by definition, probability of having the condition intersect a positive test result. We already have that number, right? Divided by the probability of a positive test result. Do you buy that, guys? This is just definitions. You know, this is the definition of conditional probability. Yes, no?
Yes.
Right? We have this upstairs number. We don't have this. We don't have this value. But what's the probability of a positive test result? Well, using Bayes' theorem, isn't it the probability of positive and having the condition plus the probability of positive and not having it? Right? Those are the only two cases where we have a positive test result. So we can just add them up, can't we? Add up these two values. Do you see that, guys?
Yes.
What do you get? Is that the 0.20 something? Oh, one too many nines. I don't know what you get, guys. You got to help me out on this.
I got. So your positive intersect with
Yeah.
don't have a result. There's actually a 01998.
Oh, you're right. You're right. You're right. So this
And
is
then what-
wrong.
Yeah.
This is wrong.
And then when you add them, you get 0.99998. 4 nines and then an 8.
I don't think that's right.
That's what I had.
Did you forget the zero here?
Oh, hold on. I did that wrong. You get 0.02097. I grabbed the wrong number.
Okay. So that's the probability of a positive test result, guys. 0.02097. Okay. So now it's plug and chug, right, guys? We have downstairs. That's what we just found. We have upstairs right there. So 0.00099 divided by 0.02097. You should get something like 0.047. And change. I don't know what the change is. What's that tell you? First off, did everybody get 0.047?
Yeah.
Did everybody else get that number too?
Yes, got it.
In English, what's that telling Kate?
Given that the test came back positive, it's the probability that they actually have that condition.
Yep. And what's that value? 0.47, right? 0.047, sorry. Is it a good test? Who said no? Esteban. Does anyone else agree with Esteban? It's not a good test? Because he's right. Think of cancer, guys. Think of cancer or a heart attack or some kind of condition that requires major medical intervention. So you go to the doc. I've been having some problems, whatever, maybe shortness of breath, whatever. So they administer a test. Okay. Test comes back positive. Oh, you've had a heart attack. Do you really think they're going to say, take 2 aspirin and let me know if you're alive in the morning? Because I'm telling you right now, they don't. They don't. And do you see this is a less than 1 out of 20 chance of being right? Do you see? No. Yeah. Well, it's a lousy test, right? Does everybody see that? This is a horrible test.
But
what if it
where
were?
did that 99% accurate come from? Because that's not.
That was given. That was given.
No, well, that number is not 0.047. You see what I'm saying? What was the 99% accurate actually measuring?
The probability that the test was positive given that they had the condition. So somebody knew in advance that they have the condition. Then they administer. This is in like drug testing, right?
Mm-hmm.
So given that they have the condition, the probability that they have a positive test result is 99%, which sounds pretty darn good. But when you do the analysis like we did, it's actually really bad. And what's driving it is this number right here, guys. The negative accuracy has to be much better than that because so many people in the population don't have the disease or the condition, I should say. So many people don't have the condition, so that negative test accuracy has got to be much, much larger. Obviously, it can't, it has to be 995 or something like that. Okay.
I'm just confused why it was 99% one way and then less than 1% the other way.
It's not less than 1% the other way. It's 98% the other way.
No, when you do have the condition and positive result.
Well, the probability of having. Oh, wait a minute. Did I screw something up? No, I didn't. This is the probability of a negative result given that they have the condition. That conditional probability is 0.01. This is the probability that a person has the condition and they get an erroneous test result.
Mm-hmm.
This is no here. Let me put it this way, Brian. I think you'll.
That would be a false negative.
This is a true positive, right?
Yeah.
This is a false negative. Yes, no?
Correct.
The test result's incorrect, so it's false. What's this?
That's a false positive.
There you go. And this is a true negative, right?
Mm-hmm.
You probably have heard these terms before. Well, that the data on that's wrong. It was a false positive, right? When you're checking something out or something like that.
Yeah.
If you're looking for something. So the problem is there's too many false positives. What's driving this number? Well, in part, it's this. accuracy, and the fact that such a large number of people in the population don't have the disease to begin with.
So you have a large volume of false positives, not
Yes,
necessarily
yes.
percentage.
Yes.
Got
Well,
it.
yes and no. Yeah.
Relative percentage. but
Relative, yes. Yes. And guys, do you see that this hopefully would never, ever, ever, well, I guess with, snake oil salesmen and stuff like that, but in the true medical profession, one would hope that this kind of test would never, ever make it to market, right? If you tell somebody they have cancer, I don't care if it's, treatable. Hey, it's no big deal. We'll zap it with some radiation, whatever, right? I don't care. You tell somebody that they have cancer, that's a life-changing statement.
Yes,
Okay?
absolutely.
It there's the guys in the medical profession probably don't. Well, the surgeons don't want to hear this. The difference between a major surgery and minor surgery is? Do you know what the difference is?
The cost.
Minor surgery is surgery on you. Major surgery is surgery on me. That's the difference. You see what I'm saying? It's a matter of perspective.
Oh, yeah.
So if you're the guy that has cancer, yeah, it's a minor procedure. Yeah, that's easy for the doctor to say. It's my body. It's major, right? All right. Guys, do you see what's going on? That's why the test is so horrible. Okay. You know what? Okay. Yeah. We got a few minutes left. Are there any questions on this problem? I really like it because it touches so many different things. And hopefully it makes you think a little bit. And I hope it's obvious to you also that instead of people, if it were like electronic equipment or software, and the same numbers applied to a test that you were going to subject a piece of equipment to or a system to, if these numbers were the same, you would still have a problem on your hands, right? Right? Because you would think, yeah, because your testing methods are wrong or need to be improved, I guess. Okay. But when it comes to people, that's when these numbers really need to be borne out. Anyway, but now you kind of know. Hopefully, that gives you a tiny bit of insight as to. And I'm not defending the medical profession. Okay, I am not. But in order to flesh out all these numbers and make sure that this type of thing doesn't happen, that's why they have to undergo all these tests before something is approved for, general medical use. So you'll find that out when you have medical conditions. And well, there's this new experimental thing, but it's not approved yet. So we can't do it on you. That actually happened to me. Anyway, can I reboot the board?
Yes.
Oh, we have to do some homework. I want you to take a look at some homework problems before Thursday. I forgot to give you some, sorry. What homework are we up to? I have to grade some too.
3.
For you.
Number 3, yeah.
Well, we'll make it due in 2 weeks. What's today?
19.
The 19th. So
this will be due on the 3rd. Second?
second.
Where's my book? I had it out. What did I do with it? What did I do with my textbook? Oh, crud. Did I put it in my bag, in my satchel? I bet I did. Well, shucks. I think it's not my car. Or is this it? There it is. There it is. There it is. There it is. That's the problem with doing a remote-only class and an at-home class or a blended class, because I have to go to school for the other class. Let's do in my book it's numbers it's after section it's after the last section in the book, after section 2.6. $72, $75. You're going to love this one. $79. This one should be easy for you. $85. 87 is kind of tricky, but we can do it if you bring it up. If anyone has any trouble, yeah, just look at these, okay? Take a look at those before Thursday, and if you have any trouble, bring them up in class and we'll do them, okay?
Is that 73? 75?
73, 75, 79, 85, and 87.
Okay, thank you.
Yep. The answer's in the back of your book. All right. Now, we only got like 2 minutes left. It's probably not worth doing much for chapter 3. We're going to pick it up here on Thursday. Okay, guys? Again, take a look at these exercises though, please, before Thursday, and just, you don't have to do them. Just make sure you know how to do them. Okay.
Okay.
All right.
Can I ask you a quick question about the homework we had for today?
Absolutely. Yeah.
Number 55 was item numbers that start with 3 letters and then have 4 numbers. And it was
Yeah, I remember that one.
probability that you'll grab an item that begins with a vowel and ends with a 7.
Yeah.
I just cannot set that one up to get the right answer.
3 distinct letters followed by 4 distinct non-zero digits. Is that right?
Correct.
Okay. It all boils down to whether 0 is even or not. What I got, this is how I did it, and I think can I get rid of this, guys?
Yeah.
Yeah.
Did the book get 20 out of 160? 20 out of, oh boy,
It was like 10 out of
117?
yeah.
Okay, yeah, I know how they got the answer. It depends on whether you consider 0 even or not, I think.
Wasn't it just taking into account digits 1 through 9?
Yeah, I thought they were non-zero.
Oh, okay, that's right. I remember now. Okay. So 3 distinct letters. These are all letters, yes, now?
Yep.
Okay. How many choices for the first?
5 for vowels.
Well, in general,
Okay, 26.
right? 26, 25, 24, because they're distinct. 4 distinct non-zero digits, right? This is in general. So this is going to be our denominator, right? So 4 distinct digits, right? So 9 choices for the first one because they're non-zero,
Okay.
right?
Yeah.
Okay, so you got to multiply all these. Okay, now what we're after, which is our favorable, number of favorable, we're after first letter of vowel, the number of ways to match what we have. So this is a vowel. So we have 5 letters that are, oh, it also depends on whether you consider Y a vowel or not, right?
Right.
But to get the answer in the back of the book, you need 5 vowels. And if we pick one of the letters to be a vowel, that means we have 25 left for the second, 24 left for the third letter. And then last digit even. So we have 9 choices for the first one because it doesn't matter. 8 for the second one, 7 for the third one. And the last one, we have 4 choices. Is that true? That's definitely the way to get the answer in the back of the book. Although, do I agree with that? I'm not sure I agree with that. Because
Well,
what
the
if
first 3 were odd?
one of them could be even, right? In fact, given this sequence, at least one is even, but 2 could be even too, right? What if we chose 8, 7, 6 for these 3 numbers? We'd only have 3 choices here. I'll tell you one thing, if you multiply this value, divide this value, these numbers are all multiplied together. If you multiply this number and divide it by these numbers multiplied together, you get, so this divided by, right, that equals 20 out of 26 times 9, which is 10 out of 117. And I'm not sure I agree with it because I don't agree with that number right there. I'd have to think about it to prove it to myself. But if you do this math, you get what's in the book. I do know that.
Yeah, I was screwing up. I wasn't doing n-1, for distinct values.
There you go. There you go. Yeah. Yeah.
All right. Thank you very much.
Yeah, I don't know if I cleared anything up, but I tried.
It's good.
I'm going to have to think about that. I really am. And the last digit even. I'm going to have to think about that. All right. Any other questions? Oh, that's right. Does somebody else have the OBS? Can somebody else look into downloading OBS? If somebody reminds, I have it on my laptop. If somebody reminds me, I'll